Hi, Mr. T here. Welcome to this video. In this video, we're going to go over the 2022 paper for achievement set of 91390, how to demonstrate the understanding of thermochemical principles and properties of particles and substances. Now, the reason for this video is just to give you an example of how you might answer this paper. Also, I've tried to make the answers more clear than they would be in the marking schedule. You'll get up NCEA. Remember, this is standard 3.4, and look, if you find this useful, have a look at my other videos. There's 2022 one on 3.4, and I'm going to make some other ones on 3.5 and 3.6. Right, hi, it's Mr. T here. In this video, what I'm going to do is go over the exam. So specifically, when I talk about the exam, I'm going to go over the paper for Chemistry 3.4, demonstrate understanding of the thermochemical properties of particles and substances. This is 2022 paper, and it's for achievement standard 91390 for NCEA level 3. Okay, so let's have a look at this paper. I'll get to the first page. Sorry, I'm on the first page at the moment, so let's have a look at this. The first question they want us to do is to draw the Lewis structure and the name of the shape for the molecules here. Now, last year in level 2 we had to draw Lewis structures, but the central atom could only have or accommodate around it 8 in total electrons, or 4 pairs of electrons. So now we're able to put 5 or 6 pairs of electrons around the center, so all extra electrons are placed around the center. And remember, the first step we do when drawing Lewis structure is to count the total number of electrons. So both bromine and chlorine are in group number 17, but we just abbreviate that to 7 of the tall groups. So we have 5 chlorines and 1 bromine. That's 6 times 7, we have 42 electrons. So we will place bromine in the middle with the 5 chlorines around the outside. We give each chlorine a bond and then fill in the rest of its electrons, so it has 8. Remember, each bond represents 2 electrons. And once we've allotted each of the 8 electrons to each chlorine, that is 40 electrons. We have 2 left, we put them around the center. Now, because this has 6 electron density regions around the center, we know that the base geometry of this is an octahedral. So because this is octahedral shape, but 5 of the regions are bonding and 1 is non-bonding, we know that this is a square pyramid. We have to learn these shapes. The next one, again, if we want to draw the Lewis structure, we have a bromine and 3 fluorines, so that's 7 times 4, 28 electrons. We're going to put the 3 fluorines around with the bonds connected to them, and then the extra electrons around them. And then we have, that's 24 electrons we've used in total. We put the other 2 pairs, or the other 4 electrons, around the central bromine atom. So now we have 5 electron density regions around the bromine. That gives it a base shape of trigonal bipyramid. And if we have 3 bonding regions in a trigonal bipyramid base shape, we have a T shape. Now, in this case, if you get one of these rows correct, you get achieved. If you get all of this correct, you get a merit. Okay, so the next question is, we've got tellurium tetrafluoride, TeF4, has the following Lewis structure and shape. It's got 5 electron density regions we can see here, and we have to explain the polarity. In order to do this, we need to include an explanation of the shape. Now, this is fine. I've got 2 acronyms I use to work this out. The first one is DRASBO. CERASBO I use to remember all of the key words I need to include in my explanation of shape. The first one is I need to include what the central atom is, that there are electron density regions around the central atom and how many. I need to say that these regions repel for maximum separation, that the angles that they produce, the base shape or the base geometry, I need to include that. I need to say how many are bonding and non-bonding regions, and their overall shape. So the CERASBO, if I write this down or if I remember this, I can check that I have each of those important points. Now that's to explain the shape. If I need to then go on and talk about the polarity, I have another acronym that I use, which is UBAC, which is EUBAC. I want to mention the electronegativity, that two atoms unevenly share electrons, that a bond dipole is produced, and then we need to talk about either asymmetric or symmetric, and they cancel out or don't cancel out. So let me show you how I do this. So in this Lewis structure here, the central tellurium atom has 5 electron density regions around it. So there are 5 electron density regions around the central Te atom. These regions mutually repel for maximum separation. So center electron regions repel for maximum separation and produce the angles. Now, because there are 5 electron density regions here, the angles that we produce are both 90 degrees up and down and 120 degrees around the middle. And the base shape of, this is the base shape of trigonal bipyramid. But since 4 of the bonding regions, there are 4 bonding regions, then the overall shape is seesaw. So I've now included all of these points, and I'm quite happy that I've explained this. The next part is I need to say, well, is it polar or non-polar, and can we explain why? Okay, so the first thing we look at is the bonds here, and the bonds are between tellurium and fluorine. Now, fluorine is the most electronegative atom, so we know that it's going to take its biggest share of the bonding electrons. It's going to unevenly share the electrons with tellurium, and it will produce a bond dipole. So we write down that it's more electronegative, it has a larger share of these electrons, so I've done these first E and U parts, produce a bond dipole, B. Now we talk about not the atoms arranged around the central atom, but the bond dipoles. There are 1, 2, 3, 4 bond dipoles. They are arranged asymmetrically because this shape here, okay, is a seesaw shape, and seesaw shape is actually an asymmetric shape. The only symmetric shapes that we know for our 5 electron density regions around the center and the 6 are trigonal bipyramid, octahedral, and square planar. So this, as these dipoles are arranged asymmetrically in this molecule, they do not cancel out and the molecule is polar. Now, if we include all of these parts, we're going to get the excellence. If we only explain one of these components, so if I explain the shape right, I'm getting the merit. If I explained the electronegativity correct, sorry, not electronegativity, the polarity correctly, I get a merit as well. So, I mean, you only get 1 merit, but you have one of them right. You can get 2 achieve points. 1 achieve point is basically saying that the number of electron density regions influence the shape, and the other achieve point is that you recognize that electronegativity is involved with producing bond dipoles. So you should write down, even if you don't remember the whole thing correctly, you should start writing down what you can, because there are ample opportunities to collect marks here. Okay, let's look at question C now. Oh, sorry, question B is always going to be, and question A is always going to be in our exam. Question C is in there about 2/3 of the time that they make this paper. Now this is a colorimetric experiment. So we are heating a liquid with a fuel source. We need to work out how many moles of fuel was used, and we need to work out how much energy was needed to increase the mass of water that we have in here. It's usually a water liquid. So a student burns 2.28 grams of liquid methanol. So this is the fuel that's been used, and we've used 2.28 grams. So this is the mass of fuel used. To heat 100 grams of water. So what is actually being measured is the change in temperature of the water. So 100 grams of water is the mass of water that's been heated. It says the initial temperature of the water was 20.6. Once all the methanol was combusted, the student correctly determines the experimental enthalpy change for the combustion of liquid methanol equals 68.6. The specific heat capacity of water is 4.18, and they've given us the molar mass of the fuel. They've given us the molar mass of the fuel because we have the mass, and we can work out how many moles were burnt. Okay, calculate the final temperature of 100 grams of water must have reached in this experiment. So let's start off with a couple of equations that we're going to use. So the first one is we're going to find the total amount of energy by working out, the total energy change equals the amount of energy divided by the moles. Okay, but our first step here is, well, I've rearranged that equation. let's rearrange this equation in that the amount of energy equals the energy for the reaction multiplied by how many moles we have. In order to solve this problem, I do have the energy for the combustion of ethanol. It's 68.6, negative 68.6, but I don't know the moles of fuel of methanol that was burnt. So if I want to work out the moles of methanol, I have the grams and I have the molar mass. So I'm going to be using this equation here. So I plug my numbers into here, and I work out that there are 0.07125 moles. Now notice I've put this to 4 significant figures. That's fine because it's a working answer. I'm going to round it to 3 at the end. So now I know that this is 0.7125. I can place it into here along with the delta RH that I get from the combustion equation. Okay, so this is the enthalpy for this combustion equation. So I'm going to take this equation here and I'm going to substitute the values in. And overall, I get an answer of minus 4.888 kilojoules. Again, 4 significant figures, because I'm following this number through, I'll round it later. Now, because negative Q equals negative 4.88, Q equals 4.88. Now, the other thing I want to do, in order to put this into what's going to be our heat capacity equation, I'm going to have to convert this to joules. To convert kilojoules to joules, I multiply this number by 1,000. And remember, I am cancelling out the 2 negative signs. So the answer I get here are 4,888 joules. That's the answer for Q. Now we go and grab the last equation that we have for working this out, and that is that Q equals the mass times the heat capacity times the change in temperature. Now at the moment we know what Q is. We know the mass of the water that was heated, 100 grams, and we know the heat capacity, 4.18, because they've given it to us. What we don't know is the change in temperature, and that's fine because that's what they've asked us to find out. How hot has the temperature reached? We can only work that out when we find the change in temperature. So in this case, what we have is we're going to substitute in these. Actually, let's rearrange this equation first. I'm going to keep T on one side and move the MC to the other side so it divides, and we get the change in temperature equals Q over the mass times the heat capacity. That equals 4,890 or 4,888 if you had kept the working value in your calculator. Divide that by the mass times the heat capacity of water. Remember, if you are putting this straight in your calculator, put the brackets around this so it doesn't divide by 100 and then multiply by 4.18, and the answer I get is 11.7. That's not my final answer, that's how much it changed. I then add 11.7 to my initial temperature, which was 20.6, and my answer is going to be 32.3. Okay, so the answer here, 32.3. Right, so I've just written in 32.3 for us. I didn't have that ready to go on my PowerPoint here, but so that's the final answer. And in here, we're going to get, wait a minute, let me see if this is, get this onto the clicker. Let's see if I can get this going. Okay, so achieved, merit, excellence. If we get one of these parts correct, we're going to get the achieved. If we get the correct process with, and it's quite a long process with one error, so let's say I only put 11.7 degrees Celsius instead of taking it, adding it to the 20.6 at the start, I might only get the merit. If I get the final answer to 3 significant figures and the correct unit, which is 32.3 degrees centigrade. Actually, for this, they accept 2 to 4 significant figures, even though we're supposed to give it to 3. So if we do all of that, we get the excellence point. Okay, so the next point is, why does the standard enthalpy combustion of methanol is significantly more exothermic than experiment value provided? So that is not the value, the correct answer. What's the 2 reasons for this difference? So they asked for 2 reasons, but they really only have 1 reason, and they give you the answer here if you give 1 good reason and explain your reasoning. So the reason is the calculations what we're actually measuring is the heat that went into the water, but not all of the heat from the combustion goes into the water. Some goes into the container of the burner, some goes into the tripod, some goes in the gauze mat, some goes into the beaker, the glass of the beaker, and some goes into the air environment around it. So it's only measuring a proportion of the heat, and the rest of it is going into the surroundings. That's my reason. And for this one here, they're going to give us an achieved and a merit for that answer. Right, achieved for saying, okay, there's some heat going somewhere else, and then merit for saying, well, because there's heat going somewhere else, we're only measuring a fraction of it. Okay, let's go to the last. Oh, this is the end of this question, and you can see here for this question, we get, if we get the two E points, which is this description on the left and this calculation, we get an E8. If we do a little bit wrong, we get an E7. So if we have a minor mistake, and if we, I guess, get 1, 2, 3, 4 merit points, we've got an M6, and 3 of the merit points gives us an M5. And we just calculate the achieves based on how many of the A's that we get. Okay, let's look at the next question. Question 2. Complete the following table. Okay, so we're going to write the electron configurations for atoms. Bromine is a straightforward, but it's quite a large one. So bromine is, what's that, number 35. So we're going to put 35 electrons in these sublevels in order. Now notice I put argon for the first 18, and then I've written 4s before 3d because that's what I do. That order of those two doesn't really matter. I put 4s because it comes before 3d when filling them, but numerically the 3d would go first. And we've got 4sp there. Vanadium, it's atom number, let me think, is it atom number 22, I think? So we have 23. So we have the 18 electrons from argon, we have 2 electrons in our 4s orbital, and then the 3 remaining electrons in the 3d orbital. For nickel, it's an iron 2+. So the rule here is you need to remember that transition metal ions, cations here, they lose the electrons in the 4s orbital first. So you should have no electrons in the 4s orbital. So nickel usually has 28 electrons, but in this case it's got 18. We removed 2 to make it a 2+ ion. The 2 we removed were the 4s electrons, so we've just got electrons in the 3d8 orbital. Now you get an achieved here if you get 2 out of those 3 correctly. Now we move on to question B. Question B is sort of turns up every second year. It's turned up 2022 this year, hasn't turned up 2021. I know that in 2023 it didn't turn up, may turn up in 2024. So this is a heating curve for a molecule, it's ammonia. And now the important thing we need to remember about these heating curves is that as the temperature increases, the kinetic energy increases, right? So what's happening is the particles are moving faster and they have more kinetic energy. And temperature is a good indication of the kinetic energy, or it is actually the measurement of the average kinetic energy of the particles. As we have a stop in the increase in temperature along the horizontal lines here, what we're happening is we're breaking bonds. Okay, so but that's an explanation here. We're going to write that on the right hand side. The first part we have to do is write a fusion equation. Now fusion equation is when a solid turns to a liquid. So even though it uses the word fusion, which would mean is coming together, in this case it means a solid going to a liquid. So we write NH3 solid plus we have the NH3 liquid, sorry, not plus, arrow to NH3 liquid. This is the equation we're looking for. This is an achieved equation. Okay, with reference to the heating curve, explain the changes between A and D. Your answer should be refer to the energy and movement of particles and intermolecular forces of attraction. Oh, that's nice they've given that to us. To compartmentalize, to make this easier to do, we should talk about the section A to B, B to C, and C to D. So we're not just saying from A to D, but we're taking each section in. We talk about each one separately, each of those three sections. So we start with A to B. As energy is added, the kinetic energy of the solid particles increases, and their movement, if they're solid, it's a shaking or vibrating movement, increases. And so does the temperature, right? So what's happening, because the shaking or movement's increasing, the temperature increases. So that's all that happens here. But when we get to B, you can notice that the temperature stops increasing. So the energy being added between B and C is used to break intermolecular attractions. It breaks a small proportion, maybe a third, maybe 40% of the attractions between the NH3 particles as the state changes from a solid to a liquid. No energy is being used to increase the kinetic energy. So there's no increase in the movement or the kinetic energy. It's just using that energy to break the bonds, because bond breaking is endothermic, so it needs to absorb energy to break those bonds. Okay, C to D is exactly the same as A to B. That is, the energy added is increasing the kinetic energy of the liquid, because it's a liquid now between C and D, right? So we've changed from B to C. We've changed, all the particles have moved from being a solid to a liquid, and now from C to D it's a liquid, but the particles are moving faster, increasing their movement, so their temperature increases. That's what the energy is being used for. This is 2 achieved points, 2 merit points. Let me go over these. So do you identify that the particles are gaining kinetic energy for A to B? Yes, that's an achieved point, right? Or from C to D. Did you recognize that energy is used to break bonds in B to C? That's another achieved point. So those two separate things, it gives you an achieved point each. Did you link the change of kinetic energy to the particle movement? So did you say, okay, so we're getting more kinetic energy, so the particles are moving faster? That's a merit point. Did you link why the temperature does not change in B to C? Did you say, okay, B to C, there's no change in temperature because the energy is being used to break the bonds, right? So no energy is being used to increase the kinetic energy here. So I could have gone over further in my second paragraph, or my second bullet point, as I could have said, no energy is being used to increase the kinetic energy. So therefore, no, I guess that's fine. That meets some merit requirements. Excellence, fully explain all three of those points. This is actually quite a lot of marks given for a very small question. Very interesting. This 2022 was still on the last year. I think there was some of the COVID lockdowns, and we still had a significant number of students who didn't get as much teaching they could have. So these, you might find the 2022 is a bit different than the 2023 examination. Okay, let's look at the next page. This page is where we're going to calculate the enthalpy. So they've given us an equation. It's diborane, it's called, reacts with oxygen, it catches fire, the reaction is below. Diborane plus oxygen, makes boron oxide plus water. Calculate the standard enthalpy, delta RH for this. Now notice for this, notice each one of these points here, here, are all formation values, right? So they're values for the formation of these molecules. Now what that means is we can use this equation to solve, to get our answer. So what we're going to do is we're going to write in the total of the products, the total of the reactants, minus the total of the reactants, and we're going to get an answer for delta RH. So notice also here that water is in the element form, it's by itself, and it's in a gas, which is, not water, oxygen is by itself as a gas. So this here is going to be a 0 value for formation. So, and notice also that water, there are 3 water molecules. So when I fill this out, delta RH equals the value of the products first, which is the first product is this diborane, which is diborane is this one here. products. First one, diborane. That's not diborane, this is boron oxide. So we're going to take boron oxide. The value is negative 1,274. And then we have 3 waters, so plus 3 times negative 286. And then we subtract all of the reactants, which is this value for diborane, 41, positive, plus the value for oxygen, which is 0 because it's in its element form. We then simplify these and we get delta RH equals 2,132 minus 41. Okay, so we've just simplified or taken the values out of the brackets, and we get an answer of delta RH equals 2,173. Now, if you get the correct answer here with the correct number of significant figures, which is negative 2,170, you get a merit. If you made an error, now an error could be something as simple as missing out the 3, but everything else is correct. So if one of these values is wrong, you get an achieved. Now they say that you need to write this to 3 significant figures, but they accepted 2 or 4 significant figures as well. Okay, so justify in terms of entropy changes of the system and surroundings why the reaction occurs spontaneously. So in this case, we are going to break this down to talk about the system, we're going to talk about the surroundings, and then we're going to talk about, well, what would it be like in order for it to be spontaneous? So when we look at the system, what we're talking about is the equation. So the equation on the left here, we're looking at the number of gas particles. And what we can see is on the left, there is a lot of gas particles. So it's very disorganized, the matter and the energy. And on the right, it's gone to solid and liquid. It's very organized. So we have a general decrease in entropy, right? So the system has a decrease in entropy as there is a decrease in gas particles from 4 to 0. I'm being specific here across the reaction, decreasing the dispersal of matter and energy. Okay, so that's kind of a statement we just chuck in there. It's decreasing the dispersal of matter and energy. If it was the other way around, we would say increasing. So that's what's happening to our system. What's happening to our surroundings? Well, in order to know that, we need to look at the delta R value. And it so happens that we calculated the delta R value. If you hadn't calculated the delta R value, if you hadn't been able to do this equation over here, you just carry forward whatever your answer is, or you state what the delta R value is up here. So in this case, we know what it is. It's negative 2,170. So this means the energy is going into the surroundings. That increases the kinetic energy of the particles and increases the dispersal of matter and energy in the surroundings. This will increase the entropy because it's making it more disorganized. So we've got the first part is we've got a decrease in entropy, and the second part is an increase in entropy. But they've told us, why does the reaction occur spontaneously? We're going to say, well, obviously the increase in entropy of the surroundings is larger than the decrease in the system. That means an overall positive entropy, and therefore we are going to have a spontaneous reaction. And those 3 points are what lead to the excellence for this. Basically, you have an increase in mark for each of these points you get correctly. So you go from achieve for 1 point, merit for 2 points, and excellence for 3. This type of question comes up every year, and it's the same format. It's just difficult to get your head around for a start, but if you keep practicing these, you'll become really good at them, and it's a good place to get marks in. Okay, and so we go back to here again. 2 E's give us an excellence. An E with a slight mistake gives us an E7. Sorry, 2 E's for an E8. 4 M's for an M6 and 3 M's for an M5. Okay, so question 3, last question. Part A, explain why the radii of chlorine atom and the chloride ion are different. So here we're given the radius of the chlorine atom is 99 picometers, and we're given the radius of the chloride ion is 181 picometers. Now a picometer is like 1 times 10 to the negative 12 meters. It's not important. We can just see that the chloride ion is a bigger radius than the chlorine atom. Now, the first thing that I would state here is that because they're both chlorine, they both have the same number of protons. Because it's turning into a negative ion, they're both going to have electrons in the third energy level here, or in the same energy level. So that's the first statement I would make here. 17 protons, valence and electron in the third energy level. Because of this, these factors will not affect the radius. Okay, so things that might influence that, electrostatic attraction or shielding, it's not going to make a difference because they have the same amount of that. So I'm just putting that there as a statement to make sure this is not what is important here. But what is important is you're adding an extra level to, extra electron to the third level. So, and what they do is when you put the electron in, they just want to push apart from each other or mutually repel. And when they do that, they expand and the radius gets larger. So what we're looking for is mutual repulsion or mutually repels, and therefore they expand, increasing the radius. Now this is achieved in merit. I would make sure that I put down what was not important and just get that out of the way first, and then explain what is important. Okay, so justify why both the first ionization electronegativity increases across the period, but atomic radius decreases across the period. Again here, the thing that isn't going to affect across a period is going to be the energy levels, because a period all have the same energy level. So they're going to have the same amount of shielding. I'll put that at the end. But basically, electronegativity and ionization energy are both to do with electron affinity, or how strongly the nucleus is attracted to the electrons in the valence level, whether they be the electrons we're trying to take away, or for electronegativity, they're bonding electrons. So I've made quite a long first bullet point here, almost a paragraph, because I want to define what ionization energy and electronegativity is to make sure I get my grades here. So first, ionization and electronegativity both indicate how strongly the nuclear charge attracts valence electrons. Okay, through electrostatic attraction. So I'm just putting some of these key terms, if I'm not using them, in a bracket here just to make sure they're there if they're using them as just sort of targets for the marking. Now, electronegativity indicates the strength of attraction to a bonding pair of electrons. Okay, and ionization energy is the amount of energy required to remove the first electron from the valence level. As you go across the period, the number of protons in the nucleus, and hence the nuclear charge, increases, increasing the strength of the attraction to the electrons. So I've said the trend here is we get more nuclear charge, we attract the electrons more strongly, so therefore there's a stronger attraction to the bonding electrons, right? We talked about that in the earlier sentences, and it's harder to remove an electron, and that's ionization energy. So, but what's the difference with a radius here? Well, atomic radius gets smaller because the valence electrons are attracted more strongly, so they are pulled in closer. So I'll explain that point. So really we've got three really important points: electronegativity to explain ionization energy and radius. At the end here, I've also said, hey, since they're in the same period, they have the same number of energy levels, therefore the same amount of shielding from inner level. So just I've said that extra bit of stuff just so that they know that I know that they would influence if they weren't in the same period. Okay, this is achieved merit and excellence question. If you recognized, if you were able to say that there's electrostatic attraction or attraction between the nucleus and the electrons, you get an achieved point, right? If you explained one of these trends, okay, so you explain, well, why does this trend happen? You get a merit. You have to use two of the following things to explain it, though. You need to talk about the number of protons and the electrostatic attraction between the nucleus and the valence electrons. It says here as well for this that they want us to talk about the energy levels and the shielding, but remember this is just is what is not affecting. And it's important that when we write these paragraphs, we always remember to write a full paragraph and explain that there are other things that contribute towards these a radius, electronegativity, and ionization energy, but in this case they're not important. Disclaimers really, and they're looking for that if you want to get the excellence. Okay, let's go look at the last part of question 3. Okay, so again, this question is always going to be in there. They're always going to put some molecules in here that have a combination of temporary dipole attractions, permanent to permanent dipole attractions, and hydrogen bonding. So we're really going to sift through these molecules and see what type of attractions they have. So the very first one, we can see that there is a nitrogen, 2 nitrogens, and hydrogen. So the way that this molecule is going to be arranged is as a nitrogen joined to a nitrogen, and the hydrogens must be joined 2 hydrogens to each of the nitrogens. Now we know that the hydrogens must be bonded to the nitrogens because they only have one bond that they can form, so they can't form to themselves and make a larger molecule. Anyway, so they're bonded to a nitrogen, a highly electronegative atom. So we've got 3 highly electronegative atoms to choose from: fluorine, oxygen, nitrogen. If a hydrogen is bonded to them, it makes a hydrogen bond. Because it has a hydrogen bond, it must also have some, well, it could have some permanent dipole attractions. But in this case, I don't think it does have permanent dipole attractions because this one actually is a symmetrical molecule. If you put permanent dipoles here, I wonder, yeah, I would let you away with this one because maybe you didn't know that this was a symmetrical molecule. However, when we get to boron trifluoride, we need to be aware that this, if we drew the Lewis structure for this, this is a trigonal planar molecule. Although we form boron to fluorine bonds and they have a different electronegativity and form a polar bond, because they arrange symmetrically, overall this won't be a polar molecule, so this is only going to form temporary dipoles. It doesn't form hydrogen bonds because the highly electronegative fluorine is bonded to no hydrogens because there are none. For this last one, we can see that we've got a nitrogen, oxygen, and chlorine all bonded together. They're actually the oxygen and chlorine bonded to the nitrogen, but in this case, we're going to have temporary dipoles and permanent dipoles. So, ignoring I might have made a mistake with writing permanent dipole for this first one, and we most probably would be more correct if we put hydrogen bonding in temporary dipole. We need to get 2 of these rows to correct to get achieved. Now, why does N2H4 have the highest boiling point of the 3 molecules? Pretty simple, hydrogen bonding. Hydrogen bonding is by far and away the strongest type of intermolecular attraction. So, is it only one of the molecules, N2H4 is the only one of the molecules that has hydrogen bonding. It has hydrogen bonding. Now I'm just covering my bases here because it has the highly electronegative atom nitrogen and is bonded to a hydrogen. Also, you could say there are lone pairs available on the nitrogen as well if you wanted to be more thorough. But this is enough for this answer here. Okay, so because of this, is significantly stronger, because hydrogen bonding is significantly stronger than both temporary and permanent dipole attractions. Therefore, more energy is required to break intermolecular attractions and the boiling point is higher. Remember, every time that you talk about these explanations here, okay, every time you talk about bonding and we're looking at boiling points, or sometimes we'll be looking at the amount of energy for vaporization or fusion, we need to state that more energy is required to break these intermolecular attractions. Okay, so that is a really important statement. So here, really by identifying and explaining that this is hydrogen bonding and why is an achieved point, and then saying about this extra energy requirement required to break intermolecular attractions, that's going to get you the merit point. So the last question on this paper is, why is BF has a much lower boiling point than NOCl? So we look at these two and we can see that their molar masses are the same. So that's the first statement I'm going to talk about, is since their molar masses are the same, their electron clouds are similar. Well, see, they're not the same, but they're very similar. The electron clouds are very similar, so they're going to have a very similar strength temporary dipole attractions. So BF and BF3 and NOCl have similar size molar masses and electron cloud sizes, so will have similar size temporary dipole attractions. However, Remember what we said before. NaCl has permanent dipole attractions due to the molecule being polar. BF3 does have polar bonds, but they are arranged symmetrically and cancel out. That results in it being non-polar and having no permanent dipole attractions. Now I need to say, because they have the same size temporary, and one of them, NaCl, has permanent on top of, it's going to overall have stronger attractions. Because NaCl has permanent dipole attractions as well as temporary, it's not that the permanents are stronger than the temporary, it's that the combination of the same size temporary and a permanent on top of makes the overall intermolecular attraction stronger. More energy is required to break them. This results in a higher boiling point. So here we would get 1 point for saying that have similar size temporary dipole attractions because they have similar size electron cloud because they have similar size molar mass. The second point we're going to get is identifying that overall the intermolecular bond strengths are stronger for NaCl because it also has permanent to permanent dipole attractions. And the last point would be to get, the third point here is to say again that the stronger the intermolecular attractions, the more energy required to break them, therefore the higher the boiling point. And one of those points is achieved, 2 is merit, and 3 are excellence. And that there is the end of the paper. I hope that has been useful. Don't forget to go and look at my 2023 paper on 3.4. I'll look to put up some other videos on 3.5 and 3.8. And good luck with your exams. Don't forget to like, share and subscribe if you find these videos helpful. Leave any comments if you have any questions or if you notice any mistakes. Thanks again. I hope you enjoy the video. Well, I hope that it's useful anyway. I hope that video has been useful. If you have any questions, don't forget to put that down in the comment. I'll see if I can answer them for you. Don't forget to subscribe if you want to see some other videos that I have made about this, and give it a like if you found it helpful.